ignore that, please. This chapter is all about energy. Okay, all about energy. So we're going to look at energy in terms of joules, but when you think of energy, you should think of things like calories. Andrew, focus. You should think of things like calories, okay? When we talk about energy in food, and we're going to talk about in this class conservation of energy and how energy is transferred. In the first section, we're going to look at what's called work and energy. And if you think about it, when you're like walking upstairs to get up here, you're doing work. You're exerting some sort of energy to perform some operation. Or if you're playing a sport and you're throwing a ball, or you're swinging a bat, or you're kicking a ball, or you're shooting a basketball, or passing, you're exerting a certain amount of energy in order for that ball to move, for work to be done on that ball. So the idea is that work is done on an object, and it takes energy to do that work. So the first section in this is called work and energy, because those two things are indeed related. All right, we're going to understand what's called scientific work. We're going to relate it to when it's performed and how it is a result of several forces acting on the object. In the next section, we'll talk about things you've heard of before probably, like potential and kinetic energy. And we'll talk about conservation of energy in the third section, and then power in the fourth section. Okay, and then this is going to take us into the next test, into test 4, but that won't be for about 2 weeks or so. All right? First, the definition of work. Work is defined as the product, and this is a little bit confusing, so look at the definition specifically. The product of the component of force along the direction of displacement and the magnitude of the displacement. The component of work along the direction of displacement and the magnitude of displacement. So let me explain what that means. Let's say an object is being pulled at an angle, and the object moves this way. Okay, it's being pulled at an angle like a sled or a box or anything that's pulled, and it's moving horizontally only. Only horizontally. From your test yesterday, what would I break up this FP into? How would I break it up? Yeah, FPX like this, and FPY like this. Now, what's FPX? What's FPX really? How do I consider, if I call this theta, please. What is FPX? How did you resolve it into components yesterday? What's the formula for FPX and FPY? How do I figure them out? Andrew?
mg times cosine.
That's for an inclined plane. That's the weight, breaking up the weight, right? For inclined plane. This is just an object being pulled. And FPY is? Okay, so I know this from last chapter. All right, so we have this information down pat. Now, which of these forces, FPX or FPY, act in the direction of the displacement? FPX, and think about it, right? The displacement is horizontal. FPX is horizontal. FPY is vertical. So that doesn't have an effect on this. So let's look at our definition again of work. Work is the product of the component of force. I'm going to underline this. The component of force along the direction of displacement. That is FPX. The component of force that goes with displacement is FPX. The component of force that doesn't go with the displacement is FPY. All right? So really what we're looking at is, and I'll put it at the bottom here, work is the product of, so I'm going to put 2 parentheses to show product, the product of the component of force along the direction of displacement, that's FPX, and the magnitude, I'm going to underline this in blue, the magnitude of the displacement. In the first chapter of the year, the first section of the year, we talked about displacement, and then we talked about something else that we didn't call displacement. What was the other thing that was similar to displacement but was really different? What was it? Distance. That's the D in that equation, the lowercase d up there. Remember, the magnitude of displacement is really distance traveled. If my displacement is negative 20 meters, the magnitude is just 20 meters. If my displacement is 45 meters, the magnitude is just 45 meters. So in this problem, the work is really defined as FPX times the distance. Well, if I write out what FPX is, It's FP cos theta times distance. That's what work is defined as. And if we go back up, that's this right here. FD cosine theta. This is FD cosine theta. Again, the definition of work being F times D times cosine theta really comes from this down here. All right, so in this chapter, in this section, for the next few sections on work and energy, we have to remember that the equation for work, God bless you, is FD cosine theta. Okay, again, this is always assuming that theta is between the force and the direction of motion. Please jot that down here. Theta is between the force and the direction of motion. Theta is the angle between the force and the direction of motion. The force and the direction of motion. Now, work can be negative or positive, so we're going to see as the chapter progresses that if theta is a number bigger than 90, we end up getting a negative amount of work done. And that has to do with friction being negative work, and we'll get into that. But I want you to know that theta can vary. It doesn't have to be just between 0 and 90. It can be like 150, 170, 180. Okay, it can be anywhere between 0 and 180, really. But this is our general definition of work. Now, the units here, the units of work, the units of force are newtons. The units of distance are meters. So it's really Newton times meter. But that has a definition. A Newton times a meter is a joule. That's what the definition of a joule is. Joule. Joule. Okay, not spelled like jewels, like, diamonds or something like that. Or joules Amazon, not like that either, that's true. Okay, 3 spellings for joules. A meter. Because distance is measured in meters. Yes? Joules are defined as newtons times meters. It's in the top, it's actually up there. That's what I'm pointing to. Yep. Okay. Let's look at an example to see where we're going with this idea. All right, so example 1. Nice and loud. James, read it for us, please.
How much work is done on a shopping cart when pulled 12 meters by a force of 75 newtons at an angle of 60 degrees?
All right, so we're pulling on a shopping cart. I guess it should really be push. You push on a shopping cart, but maybe you're in the front of the shopping cart and pulling it behind you. Now, at the end of this problem, let's take a look at these numbers in English systems, so we get an idea of what's physically happening, all right? So let's convert at the end. Let's do everything right now with newtons and meters and joules, and then at the end of the problem, we'll convert newtons into pounds, and we'll convert joules into calories, so we can see what we're physically doing, all right? So let's begin this problem by taking a look at the idea first. The force is 75 newtons. Here's the shopping cart. Here's the force. Here's the angle. And it's going to move from there all the way to here. And the distance traveled is going to be 12 meters. So this is how I think about this problem. It started at the beginning of the origin, if you will, and then it moves 12 meters either right or left. It really does not matter which way it moves. The angle is 60 degrees. The pull is 75 newtons. All right, so all I need to do is plug into the formula. Okay, this is one of those chapters where formulas are really easy to use. It's just going to be F times D times cosine of theta. Okay, they're going to be a lot simpler in this chapter with formulas than in the last one for sure. So the work done is 75 Newton force times 12 meters times the cosine of 60 degrees. How do I know it's 60 and not 30? How do I know I'm not going to use this angle up here of 30 degrees? Marco.
Is it
No, not ramp here. What's the definition of theta in this chapter?
Angle between the force and the direction of motion.
The angle between the force and the direction of motion. That's our definition. So, if I were pulling on this object, and instead of moving horizontally, what if I were pulling at an angle and it lifted straight up in the air? Well, then the direction of motion would be vertical, and we use 30 degrees instead. Okay, so in this chapter, we're always going to use cosine. We're not going to have to worry about sine. We don't have to worry about y and x in this chapter. All we have to remember is that theta is defined as the angle between the force and the direction of motion. All right? What do I get as a number? 450? Can somebody check to see if that's right? Agree? All right. So let's take a look at this now, and let's think about this in terms of English units. So two people, or a few people, go to Google real quick and type in the following stuff. All right, type in the following. Type in 75 newtons. Just type in 75 space N space, then the word 2, and then type in LB for pound. See if it'll convert newtons to pounds. Does it come up with a Newton pound converter? What do you get? 16 pounds? All right, so let's think about this for a second. 75 newtons is 16.86 pounds of force. So think physically. All right, hold 15 pounds in your hand. It's not that heavy. Okay, 15 pounds is relatively light. That's the force you're pulling with, the amount of force you would have to hold. Now convert 450 joules. Convert 450 joules into, and you have to write this down, kilocalories. We heard them calories, but they're called really kilocalories. KCAL. Convert 450 J or joules to KCAL. What do you got, Cooper?
I got 386.9 KCL/H times M squared.
Yikes. Let me look. Let me pull up a... Anybody get anything different? I want to convert 450 joules into calories, but with a capital C. It means kilocalories, really.
No, I got point 106.
That's what it is. What is it?
108.
0.108?
Yeah, what's all the first? No, I already said that. What's all
So, think about it for a second. If you're in this grocery store, all right, think about calories in food. If you eat like, I don't know, I'm thinking about a snack that I know the calories of. Like something like Twinkies, a lot of calories, like 300 calories in just a package of Twinkies, right? So, you pull in the shopping cart with 15 pounds of force for 12 meters. That's 36 feet almost. It's a little bit more, actually. So about 40 feet of pulling on a shopping cart with 15 pounds of force only burns 1/10 of a calorie. All right? So to get an idea as to what it takes to actually burn calories, when you're running and stuff, after you run, and usually if you run at a decent pace, you burn like 100 calories every hour, I think it is. Or no, every mile. Every mile, sorry. If at an average pace of like a 10-minute mile, every mile you burn like 100 calories. So just pulling on a shopping cart is not doing much as far as exercise is concerned, right? So you need to actually be physically pushing yourself to exercise. Just walking isn't really going to do enough if you want to actually burn a good amount of calories. Okay, just to give you a number sense of the problem, let's go to the next example. All right, question 2. Dirks, nice and loud. Go for it.
What should the angle of theta be if the force is horizontal? If the force is a horizontal force in the direction of the displacement, the opposite direction, or in the opposite direction of the displacement?
All right, so think about it for a second. If the force that we're looking at is opposite displacement, so let's draw a diagram real quick. We'll draw 2 diagrams. First, 2 separate diagrams, okay? This is not like before and after. So in the first scenario, displacement is to the right. Second scenario, displacement is to the right. But in the first scenario, it says what would the angle theta have to be if the force is a horizontal force in the direction of displacement? Well, horizontal means it's either right or left. So to be with displacement, this is what the force would look like. To be against displacement, this would be the force here. What force acts against displacement? Friction. So in these two problems, if the force is with your displacement, that's Fp that we're referring to. If the force is against displacement, that's Ff. Well, the question becomes, what's the angle? What's the angle now if it's horizontal? So in the first case, for Fp, all right, draw in a horizontal line, a dashed line right here. If two lines are collinear, what's the angle between them? So kind of a trick question. What is it? Yeah, the angle is 0. There really isn't an angle between them. They're collinear. They're acting in the exact same direction. There's no little, there's no little gap there. Where we don't have a situation where Fp is like this, right? And this would be our angle now. So we don't have that. So right now, they're collinear. So in this case, theta is equal to 0 degrees, really. But now draw one like this, please. Over here. Now, if I look at the direction of motion and the force, now I've got an angle that goes all the way back to that spot. What is that kind of an angle? How much of an angle? Not the shape. What is it? 180. Think back to geometry. Okay? If I have a vector this way and another vector this way, yeah, then they're just 0. But if I have a vector this way and then another vector this way, the angle between them is that full sweep of 180, right? So,
How is that different?
because again, ready? A vector this way, another vector this way. Is there any angle between them? But if I have one this way and one this way, to get from one to the other, you have to fully go through that whole arc of 180 degrees. So one of them acts in the same direction. When they're in the same direction, there is no angle. Now, in these problems, what I want you to do is to go in your calculator and type in the cosine of both of these angles. Try them both separately. Try the cosine of 0 and try the cosine of 180.
If you pull with a force of like 15 pounds, is that going to thing is 15 pounds?
No, it does not. The thing could weigh different amounts. The thing can weigh whatever it is. But it's on wheels, right? You're in a grocery store. So you're pulling with 15 pounds, it doesn't matter.
Does that relate to the person's force or like the object?
The person's force. The amount of force the person applies. Is what you're looking at.
So this is a scenario, right? Or on the left, there's no friction in that, or how come?
No, there is. But I'm specifically looking at the force of pull in this case, and I'm looking at the friction in this case. They're both existing in both scenarios.
Can it go? So the one on the right is like not moving, all moving back.
It could be moving, but I'm not worried about moving. I'm just asking for the angle. What do you got?
1 and -1.
Okay. -1. Everybody get 1 and -1? Okay. I know, I heard you in the beginning. I was giving others time.
That's alright. I'm not speedy. Tell her to stop.
All right, now, here's what I want to get to. This is the point that we're going to make. Listen. If an object is moving and you're trying to find the work done by a pull, it's going to end up being positive. Okay? If you're trying to find the work done by something that's acting in the direction of motion, such as Fp, it comes out to be a positive amount of work. Because when you use cosine of 0 or cosine of 20 or cosine of 30, anything cosine up to 90 is going to be positive. Anything from 90 to 180, try like anything on your calculator. Try cosine of 120. You'll get a negative number. It doesn't matter what the number is, but you're going to get a negative quantity. That's because when you're looking at the work done by friction, the work done by friction is negative. You're losing energy to friction. So when you have the cosine of a number like 180 or 170 or 150 or any angle, you're going to get a negative answer key and stop. Come on. You can't keep whispering across the room again. So So if you have an angle that's bigger than 180 but bigger than 90 and less than 180 in this range from here back to here somewhere, it's frictional work that's done. So you're going to end up with a negative quantity from friction.
So you say
Okay.
negative friction or negative displacement?
You're going to end up with a negative amount of work done as a result of friction because friction acts against motion. So let's summarize that with So in the first case, guys, I'm going to separate seats soon in this class. It's going to start next week. And I apologize to those in the front that are really quiet. But there's just, 3 people aren't even here and I'm stopping every 2 seconds. Can't talk every time I stop to pause. I'm speaking generally, not at anybody in particular. The negative work we see in this case, imagine the car is moving forward and you were able to grab onto the string behind the car and hold onto it, but it's still moving forward. You're resisting the motion. So you're acting like friction is acting, thus it's negative work. Because this angle here is bigger than 90. Take a look at the angle between here and here. That's an angle that's 90 would be right here. The angle that we're looking at is greater than 90. So it's going to be negative work. Now, in this case, the direction is this way, the force is this way, this angle is less than 90, or between 0 and 90 in this problem. So this is going to be positive work. So it all matters what the angle turns out to be in the problem. Okay, it all depends on the angle. So even in this case right here, we have a force, we have the displacement. The angle in this case is going to be greater than 90. Whereas here, we have the force acting and the displacement. This is the angle here that's going to be less than 90. So what I want you to remember is this. It's a simple summarization. If the force is in the same direction of motion, it's positive work. If the force opposes motion, i.e. friction, it's negative work. Andrew.
How is it possible that all of these things are going in the same direction? Like the two on the left.
There's a motor inside of it that's pushing it to the right, and then you're applying an external force.
Okay.
The F in this problem is not like the FP or anything, it's just a general force. So it's definitely moving to the right. They're all moving to the right, being pushed by some motor in the car. If the force is in the same direction of motion, it's positive work being done. If the force is opposing motion, it's negative work being done. Okay, think about friction as negative work. Think about FP as positive work, or producing positive work. Let's look at the last example for today to summarize these 3 ideas. And we'll look at all of them to get an idea. A student pushes on a 20 Newton desk. So that's the weight of the desk, not the mass, because it says newtons. A 20 Newton desk with a horizontal force of 12 newtons. A distance of 24 meters. Assume the coefficient of kinetic friction between the desk and the floor is 0.2. Part A says how much work is done by the student on the desk. Part B says how much work is done by the floor on the desk. Part C says what is the net work done on the desk. The net work that's done on the actual desk. So for part A, how much work is done by the student on the desk? What's the force that the student is applying? 12 newtons is the force the student is applying. The weight of the desk is 20 newtons. That's Fg. The distance traveled is 24 meters. And μk is given as 0.2. So for part A, I'm looking at the work done by the student. I don't care about the floor or friction or anything for part A. So for part A, I can think about my formula for work. Work equals Fd cosine theta. The force applied by the student in this problem is really Fp. The distance is still d. Oops, let me write d there. And then it's cosine of what angle is the question in this problem. What's the angle if a student pulls horizontally in the direction of motion? It's 0 degrees. Let me explain this. Here's the object. Here's motion. Okay, motion is that dash line. The pull is on the dash line. What's the angle between two vectors that are sitting on top of each other? It's always 0. Again, it's moving to the right. It's being pulled to the right horizontally. It's not at an angle anymore. It's pulled horizontally. So theta in this problem turns out to be 0 degrees. And you saw a moment ago that the cosine of 0 is just 1. So this equation simplifies to just f times d. Again, because cosine of 0 is just 1. You can type it in your calculator and figure it out, but it wouldn't affect the problem. So we end up with 12 times 24. Okay, which will give us 288, and the units are joules. Notice the answer is positive because I'm applying a force in the direction of motion. So it's positive work being done on the desk by the student. Now to do part B, we have to go ahead and think about what force is doing work on the desk from the floor. What force is that? Not normal force. I know you want to think it's normal force, right? Because the normal force pushes back up. But it's not doing work on it. Remember, to do work on something, it needs a distance traveled. So we're traveling left to right. What opposes motion left to right? Friction does. Friction is what happens here. So for this problem, we're looking at the force of friction now, not this FP anymore, but FF. Okay, it's still times D, and then it's times the cosine of, what's the angle? What's the angle if I go back up to my diagram, draw friction in right here, I'll draw it from the middle, it doesn't matter right now, and I look at the direction of motion and friction. This angle is 180. Okay, 180. And the cosine of 180 happens to be -1. So the answer we're going to get here is definitely going to be negative. But the question is, what is the force of friction? So we have to use our equations of forces to come up with what the force of friction actually is. So before I can finish this part B off, I need to look at a free body diagram here. I have to think to myself, all right, well this is FP, this is FF. I already have FP. I'm looking for FF. What is the definition of FF? What is it? It's mu times Fn. Very good, Marco. Good memory. All right. Now, mu is given. Mu is given as 0.2, I think, in this problem. Yeah, mu is given as 0.2. But what is Fn in this problem? What is it?
FG.
Why?
Because the forces kind of cancel. Well, no, they don't cancel out.
They do.
Because there's no acceleration. So.
Exactly. That's exactly right, Sarah. There's no vertical acceleration. So now look at your free body diagram in the y direction. Fg pulls down. Fn pulls up. So if I wanted to figure out what Fn was, I would go back and say to myself, all right, Fn minus Fg equals MAY. But this is really 0 because it's not moving vertically. So I get Fn minus Fg equals 0. So in reality, if you want to just remember, well, Fn is really Fg when there's a horizontal force. This was one of the scenarios I told you in class that Fn will always equal the weight if it's just a horizontal force or if it's just sitting still on the desk. Okay, so to determine what Fn was, we just use Fg. And Fg was given in the problem, wasn't it? What was Fg given as? 20 newtons. So Fn is just Fg, which is really just 20 newtons. So we can go back up, take this 20 newtons, which is really the weight, which in essence is the normal force, and plug it in up here for Fn. So we get, let me just put a little line here to separate this. We get work equals mu times Fn times distance traveled times -1. Again, the -1 comes from the cosine of 180. Mu is 0.2, Fn is 20, distance traveled is 24 meters, cosine of 180 is -1. What do you get as a result here? -96 joules. Okay, -96 joules. So, more work is done in the positive manner than there is in the negative manner, which means that you've overcome friction. It means that you're pulling on this object, and after 24 meters, you've exerted 288 joules of energy. Friction ate up 96 joules of energy. So how much work in the end for part C? What was the net work? The net work that was done on this object. Again, I pulled 288 joules of energy to the right. Friction pushed back with -96 joules of energy. What's the net energy or net work done to this object? What is it? 192. Right? 288 plus -96. Let's write this out. This is part C now. Net work is 288 joules plus -96 joules, giving us, what did you say it was again? Negative or positive 192. Clearly not negative. Okay, positive 192. So if you want to understand whether you did more work than friction did, you get a positive answer. Can friction really do more work than you, though? No, it can't really do more work than you. It wouldn't make sense. It would mean that friction moves it backwards. Friction just doesn't act on its own. It acts as a response or a reaction. Remember, friction only occurs because I'm pulling it to the right. If I'm not pulling it to the right and it's just sitting there, right? If this is just sitting there like that, friction's not doing any work to the object. It's when I start pulling on the object this way, friction's pulling back. That's the negative amount of work done to the object. Okay, so this is U, and this is friction. Okay, that's the amount of force that you do, or the amount of work that you do on the object, and the amount of work that friction does on the object is the negative component. So the idea here, what I want you to get from this, is that when you apply a force, and it travels a distance, you're doing work. You're doing work. Okay, that's how, if you've ever gone to the gym before and you use like those cables, instead of using free weights, you ever see the cable workout things, right? So say the cable's connected up top and you're doing like just chest presses and you push forward. You're pushing with a certain amount of force and the cable is moving a certain distance. So the further you push it, the more work you're actually doing. That's why if you did this, that's not going to do much. It's when you actually come together and you're moving a longer distance, you're exerting more energy or you're doing more work. Okay, that's how you're going to gain more muscle mass or trim back on fat or whatever it is that you're trying to do as a result. So the force applied over a certain distance is what work really is. The cosine theta part is important to know that it's the force done in the direction of motion. That's where the cosine theta comes into play. All right? So tonight what I want you guys to do is to practice 170 and 171. Now remember, please, think about this logically. If an object is moving vertically, so say you're pulling on an object like this. All right, so I'm lifting on a crankshaft like this, out of a mine shaft. The object moves vertically, doesn't it though? So now the direction of motion would be this way. So then the angle theta we would use would be this angle right here. Remember, in this entire chapter, we're defining theta as the angle between the force applied and the displacement or the direction of motion. So if I pull on a crankshaft like this, I'm pulling on this rope, and the object's moving vertically, the angle now is between the force and the vertical, not the force and the horizontal. It depends on the context of the problem. Alright, so if you see that in one of your homework problems, I think it's in this section for homework, it might be in the next one, but you're going to see that happen. Right, where there's motion vertically. The angle is the angle we're still going to use. We're still going to use cosine theta. Had we left the angle down here, we would just have to use sine theta. hand. Okay, but it's easier to think of our formula with always using cosine to make it simpler on us. I saw a hand in the back. Andrew or Marco, one of you guys had a hand up.
I just looked at, but so you use the theta between FP and Y.
FP in the direction of whatever motion is. Motion happens to be up in the case where you'd be lifting something out of like a mine, or maybe a well, or a coal shaft. You know what I mean? Out of the ground. Minor, I saw your hand pop up. Yeah, regular homework. Okay, do it tonight for tomorrow.
And you would use sine instead of cosine.
Well, if you forgot to switch the angle and you didn't use this angle right here, and you still used this angle right here and it was moving up, it's the same thing as just using sine. And the reason is this. I'll give you an example. If this angle is, say, 60 degrees and this is 30, it turns out mathematically, you'll learn this in your math class, that the sine of 60 is the same thing as the cosine of 30. So in this problem, you would use cosine still with the formula, and you would use 30 degrees. But if you forgot to switch the angle, you would have to change the formula and make it sine now and use sine of 60. But just to be simple in this chapter, we're going to say that theta is the angle between motion and the force. And always use cosine in this chapter. Okay? Again, you should constantly be updating your formula sheet. The formula sheet that you have saved in the beginning of the year, notability. Okay, we've gone through the first like 2 clumps so far. In the next clump of formulas, the first one you're going to see is work equals FD cosine theta. So these are where you might put notes on your formula sheet. On the formula sheet next to theta, you should put theta is the angle between the force and the direction of motion. So you should constantly be annotating your formula sheet and writing notes down on there. That will help you to study at the end of the year. When you have to use all the formulas for one test on the final, and you don't know which one to use, at least when you're studying for the final exam, and you're looking at your formula sheet, you can say, oh, these are my notes I wrote down. So it really is useful to have that formula sheet saved in notability and to be constantly annotated. Yeah, tomorrow.
You said angle between the force and what else?
And the direction of motion. Okay? Direction of motion.